hoy en ATRICA, el Encuentro Internacional de Diseño Computacional, Fabricación Digital y Tecnología Aplicada a la Arquitectura. En este último evento tenemos a Gwylliam Jahn. Gwylliam is the co-founder and creative director of Hologram, a design research practice and technology startup developing software for designing and making in mixed reality. Hologram's clients include leading universities, multinational architectural firms, industrial designers, engineers, and artists who are building mixed reality applications for full-scale construction, public art, architectural fabrication, sculpture, automotive design, and cyber-physical visualization systems. Gwylliam has delivered lectures and workshops at international institutions, including UCLA, ETH, SCIARC, MIT, USC, Stuttgart ICD, UCL, Harvard, Tunji, and Tsinghua University, and it's a lecturer in architecture and design at RMIT University in Melbourne. He's designed research in the fields of mixed reality environments, autonomous robotic fabrication, behavioral design systems, and creative applications of machine learning has been published in leading computational design conferences and journals, including IJAC, Acadia, and Rawhide, and has been internationally awarded, most recently for the construction of the Tallinn Architecture Biennale installation competition. Thank you, Gwylliam. You're very welcome. We felt really honored to have you here today. And please start whenever you feel so.
Great. Yeah. Thanks so much for that introduction, Isaac, and thanks very much for having me. I'm really looking forward to this opportunity to share some work with you all today. Because we've got a fair amount of time, but also because it's sort of late, and I understand you've had 13 hours of exciting talks and workshops and things already today, I was hoping that we could do this fairly informally. So the talk will go for about an hour. I'm going to share some of the work that we've been doing at Hologram, explain how our software works, give you a bit of a sort of a background and some context to some of the ideas behind that work. That'll take about an hour, but really feel free to jump in on Zoom through the chat whenever you like with a question, and we can maybe make it a little bit more like a conversation. I'm happy to pause and explain things in more depth whenever you like. And yeah, hopefully it can be a sort of a relaxed hour to cap out the day. All right, so I'm going to just share my screen and we'll jump into it. Okay, so Hologram is a tech startup. We make and sell software for essentially viewing, interacting, and sort of prototyping mixed reality applications on the Microsoft HoloLens, which is a head-mounted mixed reality display. At Hologram, we also do quite a lot of design and fabrication work with our own software. So we do a lot of projects which are intended to demonstrate what this software is actually useful for architects and designers and fabricators, artists, creatives generally. And we're really particularly interested when we do these kind of demonstration projects, which I'll share with you in this talk, in finding ways to use mixed reality to improve the skills of the people who work with mixed reality, in finding ways to make them achieve more with whatever kind of craft or trade or technique that they're using to make things than they would otherwise be able to do without access to that mixed reality technology. We're also really interested in finding ways to use digital models to leverage human design intuition. So trying to find a kind of a middle ground between having to preconceive entirely every single aspect of a design process digitally before you go make it, say with a laser cutter or something like that, and with a purely artistic process where maybe you have no real control over the way something is documented and you're just making everything up on the fly. So we're interested in this sort of middle ground between working with extremely precise digital models and just intuitively making something up in the same way that a sculptor might do. Lastly, with Hologram, we're quite interested in trying to find ways to engage with material in new ways. And I guess what that means is perhaps trying to rethink how we might work with low quality materials which aren't good enough for fabricating or using in digital fabrication, because they contain, you know, like failure points, cracks, they're unpredictable, they bend, what have you. We're trying to find ways to work with those sorts of materials, again, by leveraging human intuition in the making process and combining that with the precision of digital models to produce complex outcomes. So I'll just talk through a couple of projects which actually explore a few of those ideas. I'm also hoping to use this talk to explore the background and context that motivated us to start our company. And really that background and context is kind of a reaction to the sort of the trend that we're seeing in our industry at the moment towards industrialized construction. So companies like Katera, I'm not sure if anyone's heard of Katera before, but they're they're technically a startup that's trying to own the entire production chain for the manufacturing of buildings. Companies like Katera, they're trying to sort of standardize and automate this entire production chain so that they can extract every little bit of value from that chain and make money. And the way that they're doing that is they're able to make money by essentially making the fabrication process less risky, more precise, more repeatable, cheaper, faster. Like that's what they're achieving by implementing industrialized construction processes, you know, automating things with robots and what have you. Now, for companies like Katera, and generally speaking in this future of where we're kind of building buildings within factory environments with machines, the role of the architect in this future is going to be that of a specifier. So the architect is going to largely be selecting finishes and modules from a predetermined kit of parts that have been highly optimized for this particular production chain. That's what an architect will do. And I think that future is quite dystopian. I think that we're at risk essentially of optimizing out what is exciting about architecture and about design in the pursuit of essentially, you know, efficiency and profit. So at Hologram and in my own sort of design research, we're trying to articulate a sort of a polemical position to this future of industrialized construction. And we're doing that by developing a hybrid approach to making, which is trying to benefit from the efficiencies of digital processes while maximizing human design agency and expression. And we're calling this mass bespoke construction. And the goal here is just to broaden rather than narrow the spectrum of possible designs and the limits of what and how we build. A really interesting framework for thinking about these alternatives to current trends of standardized automation is through this sort of framework of slowness. So like the slow food movement, which maybe some of you would have heard of, and also like you know, the Romantics back in the 19th century, I think there's an opportunity to become more interested in the tradition of craft, in trying to draw on characteristics of local ecosystems and regional expertise, in trying to challenge the need for standardization and optimization just for efficiency and profit, and also in trying to kind of generally take an idealistic disposition that values qualities of something rather than just the quantity of something. And when I say quality, I don't mean production quality or quality in the sense that something like precisely achieves some preconceived idea of what it should be. I don't mean that kind of quality. I mean the kind of quality of a thing. Like you might say this sculpture by Lucy Irvine has a sort of a sensual quality or a character that's just unique to this thing and how it was made. I'm very interested in what architecture might look like if we just emphasized qualities of things rather than efficiencies of things. Now, as a kind of a, I mean, we run a company as a sort of an entrepreneur. I'm also interested in this, how this sort of romantic predilection towards slowness and privileging all the things I just mentioned in processes of designing and making can be scaled up, so that it isn't just an artistic practice. This could become a commercial operation as well. So in the same way that modular design has been scaled to industrialized construction in factories, you might ask yourself, what would architecture look like if it was just as feasible to produce forms like Lucy's, forms like these, as it is to produce modular, square, rectilinear, repeated building components? Like, what would that future of architecture look like, and how could we achieve it at scale? So it's not just a one-off, it's everywhere. I started exploring this idea through a PhD, actually, developing slow robotic approaches to architectural fabrication. And these autonomous robotic systems, like slow autonomous robotic systems, the idea was to start trying to optimize them for an ability to observe and gradually act on their environment rather than optimize them for just speed, to try to optimize them for flexibility and adaptability rather than to optimize them for repeatability, and to try to optimize them for nuance and subtlety in how they acted on something rather than for perfect precision. And to give an example of what a sort of a slow approach to architectural fabrication might look like, I think this work by Jason Payne is a really excellent example. This project's called Rawhide. It was from about a decade ago and exhibited at SciArc. And the project is essentially, it's a kind of an anti-fragile architecture. So it's constructed from a whole lot of shingles, and then these shingles behave completely unpredictably over time as they respond to the sort of specific changes in their physical environment and the specific changes of material properties. And they end up producing a kind of, again, a quality or character that's specific to this architecture that slowly emerges over time, that is a result of both the kind of intention of the architect and the designer, but also of something which is out of their control. And that is just, again, it's specific to this object and this place. It's not something which is just modular, repeated, cheap, standardized, etc. So when I began my sort of research agenda, which is all just sort of leading up to what we're doing at Hologram, I had pretty limited time and resources to explore this idea of slow robotic fabrication. And so the only way to really explore the agenda was through simulated digital worlds. So trying to essentially speculate on what might happen if you had a sort of robotic system gradually fabricating something over time, rather than literally doing that with robotic systems. Just didn't have the resources. So it became kind of important as a designer to be able to build design tools that could simulate physical phenomena over virtual timeframes. So these are some examples of little miniature worlds that are doing these things. They're simulating processes of material erosion or material deposition or flow over a landscape over time. And they're, by basically combining these simulated phenomena, it becomes possible to produce really, really complex formal objects, and to begin to speculate again on these kinds of qualities that just emerge by having some sort of, in this case, fictional simulated robotic agent take very specific actions within that environment in order to produce desirable formal and spatial effects. So again, the idea here is it's something which is slow, it's something which is specific to material behaviors, it's something which is a kind of a negotiation between the intention of a designer and just the characteristics of an environment and a material. It's something which is definitely not standardized, precise, repeatable. It's something which has nuance, specific character. And in this case, these are a bunch of sort of salt landscapes. It was the first speculation on what sorts of objects these processes might produce. Then after doing that kind of work, there's initial speculations which are all just virtual. Began also thinking about how this might work at smaller scale. So this is a project for a meeting pod at RMIT. And it was a competition. Essentially, the idea was to create a meeting pod by robotically depositing extruded and inflated recycled plastic bubbles. And those recycled plastic bubbles would be distributed in such a way that you could control various architectural effects. So things like transparency and acoustic separation and expression of lightness versus expression of weight, structural performance, creating surfaces that are flat so they're actually usable versus creating surfaces that just define the space of a subject. Like all of these kinds of architectural requirements were built into a model world, like a fictional simulation that could try to anticipate how material behavior might be able to sort of negotiate a few of those constraints. Now we lost the competition, and the reason that we lost this competition is because the jury rightly pointed out that the technology just didn't exist to build this object. It's an entirely fictional thing, and it couldn't feasibly be built by hand. Just, you know, the time that it would take to deposit these thousands of plastic bubbles by hand would basically just cost too much to do, and it would be too high risk. It would take, you know, it'd be too dangerous, it'd be too complex to document, etc., etc., etc. So we lost the competition. And then if we were going to do it with robots, then you would require new computer vision systems. You would require real-time robotic control systems. You'd require custom tools to control how the plastic is melted and extruded and inflated. You'd require digital actuators for controlling all of those things so that you actually were able to produce the design intent that solves the brief, that meets the client's brief. And so that also wasn't feasible. But I found it extremely frustrating that we were able to digitally model something, like speculate on something that was beyond our capacity to build. And I found that really frustrating. And so after completing this sort of competition, we went and tried to get some grant money and just gradually worked our way through addressing some of these technical challenges. So firstly with robotics, and then later on with the HoloLens. So the first thing that we tried to do to build this impossible to build pavilion was to solve the computer vision problem. So the robot, in order to fabricate structures like this, the robot really needs to be able to see the space that it's in. So we set up an environment where we had multiple scanners. Some were mounted to the robot, some were just set up in their environment that could produce essentially a 3D model in real time of the material that the robot was working with. And then we ran essentially like behavioral models that would control where the robot moved. So it would observe this point cloud of its environment, or actually it was a voxel grid. It would observe that voxel grid. It would run some algorithms to determine how it should move next. It would place some more material. That would then affect the voxel grid, and it would just repeat. So you have these completely bottom-up autonomous systems of fabrication. This is what that looks like running. So this was in 2016 in a workshop with Roland actually, and Cam Newnham for Roebuck. And the robot here is depositing some expanding foam. It's basically always scanning that that model that it's creating from foam, and then deciding where to place more foam following a behavioral model. The behavioral model is really simple in this case. It's just trying to put more foam on top of the foam that it can see. So you have this tower building behavior, basically. So this is something that's like extremely simple to do for a person. If you asked just about anyone to do this, just put more foam on top of the foam that's there, anyone would be able to do that. It's trivial. But for a robot, this is actually a fairly challenging task. You know, you end up having to develop a ton of different systems just to place material on top of what's already there. And so that also is kind of frustrating. You know, you're trying to teach, it's just extremely difficult to teach machines to do what is extremely simple for people a lot of the time, especially when it comes to craft-based practices where you're trying to respond to material. But essentially, we as a proof of concept, we solved the computer vision problem. It's possible to observe material and place more material on top of what's already there. That's so that got solved. And then the next challenge was to try to work out how we could extrude this plastic. So the plastic in the dab pod, we wanted to be able to control the color of the plastic. We had to control the size of the bubble that was being placed. You had to control the density of the material. There are a whole lot of things that we needed to be able to control directly from digital models, essentially, in real time. And so with a bunch of students at RMIT, we had a lot of fun building different end effectors. This one is one which we were all quite excited by. It's a filament extruder. So it's typical, it's just like a 3D printer basically on the end of a robot arm. But you have 3 or 4 like CMYK ink markers which paint the filament before it gets melted. So you're able to apply ink to the filament and then push it through the extruder head. So you end up with colored plastic while you're printing, and you can actuate each one of these markers using, you know, very simple servos which are controlled in real time through Grasshopper. So the same interface which is controlling the robot is also controlling the color that the 3D printer on the end of the robot is printing, which is really exciting. But the problem with these little filament extruders is they're just way too slow. So it would take, you know, thousands and thousands of hours to print anything at the scale of the pavilion, and so we had to ditch them. Instead, we built a proper extruder. So, you know, you essentially have like a large induction motor and a special screw for feeding melted plastic through a heated barrel. These kinds of extruders are also pretty common, like lots and lots of people with robot arms are making them. They're also pretty fun to make. Ours was very limited by having to go on the end of one of these UR10 robots, which is a pretty low payload robot, it's about 10 kilos. But what was special about our plastic extruder is we had the ability to mount custom dies on the end of the extruder. So you didn't just have to extrude a solid section of plastic like most 3D printers, but you could pretty much design whatever profile you wanted and then extrude that. So we designed a tube die that would go on the end of our plastic extruder, which would, and this tube die had a air inlet sort of built into the center of it. So you could control the amount of air pressure that was being you know, pushed into the center of this tube while you're extruding it. And when you control that air pressure with a digital pressure regulator, you can basically drag a slider in Grasshopper and change how much air is being blown into the center of this tube. So while you're extruding it, you can also be inflating it. And this was also really, really interesting. We were basically able to make these kind of inflated plastic bubbles entirely controlled through a slider in Grasshopper while the robot was printing. And they had a whole lot of characters that we didn't anticipate in our digital models. You know, essentially the plastic behaved in a far more complex way than we were simulating. It produced all of these kind of strange ridges and ribs and things like that in the extrusion, which also reinforced the bubbles. So these were extremely thin-walled plastic bubbles, like thinner than a Coke bottle or anything like that. But they were also quite strong because of the way these ridges reinforce them. And so I think there was like a really interesting opportunity here to do so many things at once. First of all, printing with tube that's inflated is way faster than printing with solid section because you're extruding the same amount of material to create way more volume. So it's a faster fabrication process. Then that also means you're using less material. So it's a far less, you know, wasteful process, which is great. What you're producing is more performative. If you're trying to create like, you know, insulation, for instance, this is a fantastic way to do it, having extruding tube rather than extruding solid section. And the material is able to have a character. So you're not just creating a copy paste of your digital model, which is what most 3D printing does. While you're printing, you're getting something else. You're getting some nuance and some effects and some qualities that are derived just through the behavior of the material as it's inflated and as it cools, which are still desirable. They're still good. They still give this object, you know, something that is something that makes it sort of, you know, that captures your attention as well as sort of being performative in many other ways. So at this point, we'd sort of, okay, we've proven it was possible to control the robot in real time. It was possible to make tools that would be able to extrude and control this plastic. it was possible to autonomously, you know, write behavioral systems that would allow the robot to fabricate structures of the complexity of that pavilion design. But this was also about the same time that we got the HoloLens. So this was late 2016 now, so about almost 4 years ago. We got the HoloLens at RMIT, and when we got the HoloLens, we realized that we could achieve all of the same things without needing to go through all of the hoops of programming robotic arms. So I'm just going to check, I don't have my chat window open, so I'm just going to turn it on now that I've got a second. I'm going to try and I'll check this chat every now and again. So if you guys do have a question or want to interrupt, either just turn your microphone on and interrupt me or ask it in chat. But I'll try to check it. Yeah, so we got the HoloLens, and what I wanted to do is essentially show you really a very behind the scenes look at what we did with the headset when we first got it, because often in these sorts of talks, you only show the things that work really, really well. You don't show the failures or the stupid ideas that you have when you first try something. And I thought this is a good opportunity to actually share those with you. So one of the first things that we did with the headset was, let me just make sure that plays. We thought, okay, well, maybe we can invent new sort of 3D printing processes. So maybe we could print with river pebbles, which are all these sort of strange and different shapes, and hot glue, rather than printing with, you know, entirely predictable standardized materials. So we got the HoloLens, we modeled some sort of weird little blobby thing that we thought would be difficult to build without the HoloLens. Then we got some river pebbles and just experimented with different ways of communicating in mixed reality how to make this shape. So what you see here is we're just looking at one section of the shape at a time. It's sort of like one layer, I guess, of these river pebbles. And we built some software that would just let us fabricate things like this as easily as possible. So what we figured out very quickly that we needed to do was, we weren't really sure what information we'd need to build these objects. We didn't know if showing a contour like this was going to be best, or showing the whole model would be best, if coloring it would be useful, or if we should show it as a point cloud. We didn't know if we'd want to change things, move it around. All of these were just unknown. And so we had to make some software that let us make all of these changes to what we saw on the headset as quickly as possible, so that we could test ideas and work out like how the headset was actually going to be useful to build things. What we initially did was we sort of mocked up a way to stream Rhino models to the HoloLens. So what you see in Rhino, you would see on the headset. And then with a bunch of students at RMIT, we sort of tested this out building different structures. So you would model something in Rhino, you'd look at that same model on the headset, and then you try and build it. And what that let us do is like basically eliminate all of the complexity of which is normally goes into sort of any sort of digital fabrication process. So ordinarily, if you're doing something with digital fabrication, there's a ton of work that goes into, like, you know, rationalizing your design into 2D parts so you can laser cut it, or designing funny little connection details so you can join 2D parts together. You know, all of this is very skill intensive and results in a really steep learning curve. And by instead just allowing students to draw something and send that over to the headset and then just fabricate it by soldering little bits of steel rod together, it meant that this kind of feedback loop of designing and then building and then learning was just way quicker, which meant that you could develop skills also much faster. So it eliminates this kind of stuff, you know, where you might have a whole bunch of digitally fabricated parts, but then you just have tons and tons and tons of drawn documentation that really shows in a very complex way how to assemble those parts together into some object. Like, we basically want to avoid this as much as we can when you're working with mixed reality. So working from holographic models, we found, could invert the problem space of fabricating complex designs. And so by that, I mean, when you can see exactly what it is that you're trying to build, while you're making it, it becomes possible to approximately build just about anything very easily. Doesn't matter how complex the form is, you can always approximately make it, and that's always really easy. And ordinarily, like with both traditional fabrication approaches and digital fabrication approaches, making things which are complex is usually all or nothing. So you either get it exactly right, and that's usually very difficult, or you get nothing if the part fails. It's not really possible usually to make things approximately, because that usually introduces a cumulative error. So to give you an example of this is one of the first projects that we made out of construction scale materials with the Hololens. It's 10 mil mild steel square bar. And this was a sort of just a quick digital mock-up for a chair designed in about 20 minutes. And it's very quick to design because there's no rationalization. It's all unique parts, everything's intersecting, everything's in 3D, nothing's in 2D. There's really no fabrication constraints in this model whatsoever. It's just a 3D sketch. But it captures some design intent. You know, it captures like how big things should be, how the top of the chair should work, what the formal language should be, how the structure should work. All of that's in this sketch. And we were just interested in, I guess, trying to work out whether or not you could just capture that design intent in a physical object as well, just by using this sketch as the only fabrication information viewed on the HoloLens. And this is what we managed to build in about 7 hours using a acetylene torch, like you see here. So you're wearing the HoloLens, you can see what the design is supposed to be. You're heating up some steel and just bending it into the shapes that you see on the headset. It's extremely simple fabrication process, and so it's extremely fast. So we didn't end up using a single drawing. There was no measurements, there was no templates, there was no jigs, nothing was laser cut, nothing was done robotically. Everything was just done by hand with an oxy torch, and that's it. And the important thing to point out here is that this fabricated object, as I mentioned before, is approximate. Like you can see these two things, they're slightly different, right? And that's deliberate. We're not trying to make something exact, because making something exact is very time consuming, expensive, challenging, difficult. We're trying to make it easy as possible, as quick as possible, to make something approximate that captures the design intent. And the reason that the objects aren't quite the same is because while we're making it, you're slightly changing the design in order to keep it easy to build. So we're slightly moving parts around whilst always making sure we're actually capturing the design intent. You can always see what the finished object is supposed to look like. So if you change one part, you have to make sure it's still capturing that design intent. So it's a deliberately imprecise object. This idea of making in mixed reality is definitely not actually new. Like we didn't come up with this idea. It's not our brilliant conception or anything. Like the idea of using mixed reality to make things has been around since the technology's conception. So two engineers at Boeing in 1992 first came up with the term augmented reality, and that was used to describe a system for assisting with the manufacturing of aircraft wings. And basically how it would work is a manufacturer wearing a headset would see a tiny, tiny amount of digital information that would help them carry out an otherwise kind of challenging, tedious, difficult task. In this case, it's like showing where to drill a hole in the fuselage of a part of an aircraft. So the idea is that you upskill the worker, you provide them with confidence, you reduce the risk of mistakes, you make a task less tedious, you increase the expertise of the worker with like the most minimal digital environment you possibly can. And we definitely treat this as gospel in everything that we do with mixed reality. We're always trying to do those exact same things. How can we help somebody work better using digital information in mixed reality? Now, so that was back in the 90s. So when you fast forward to 2020, mixed reality is now just mainstream technology. It's all over construction sites. This is an image from Trimble showing a BIM model overlaid over a construction site to basically facilitate quicker site walks and quality assurance checks. So this image is a mixed reality experience viewed through a mobile phone. and it's using basically like satellite positioning so that it's precise enough for those applications on construction sites. However, no one's actually, or very few people at least, are building directly from these mixed reality models yet. Like that's what we're doing at Hologram. That's still fairly unique to what we're working on. Mostly they're just used for checking things after they've been built. Now, compared to these mobile phone experiences, which are fairly commonplace, what we generally work with is the HoloLens, as I mentioned before. The massive advantage of the HoloLens over the mobile phone is that you wear it on your face, and so you can still use your hands to interact with your physical environment. You don't need to hold a phone in front of you, and you see holographic information with accurate depth perception. So you really experience things in 3D. You're not experiencing them as a 2D projection onto a screen, which again is essential if you're trying to use that holographic information to place something in 3D space. It's really hard to do from a 2D screen. It's really easy to do when you can see it in 3D space. The HoloLens is also a self-contained computer, which means that you can put it on your head, you load up Hologram, you load your model, and then you can just work. You don't need to have any extra sensors set up. You don't need to have any cables plugged in. It's literally like a high power mobile phone that you can view through a see-through 3D lens. The challenge with the HoloLens, though, is that most of the people who have great use cases for the HoloLens, so that's like, you know, designers, engineers, construction workers, tradespeople, artists, craftspeople, makers, you know, people who do build stuff, they're not actually able to easily work with this headset because the HoloLens is an enterprise piece of hardware. To use it, you need to write your own software, generally speaking. That requires skills that most of those creatives don't have. And so this is the problem that Hologram is really trying to solve. So what Hologram does as a piece of software is it just reduces the time that it takes for creatives to prototype and evaluate ideas in mixed reality by allowing them to use the design software, which they use on an everyday basis, with the HoloLens or with mobile phones or with the Oculus Quest headset as well now. So basically, just from Rhino and Grasshopper, you can build some pretty powerful mixed reality applications. How that actually works is really, really simple as an idea. So the geometry from Rhino and Grasshopper gets streamed over to your mixed reality device in real time. And if you change it in Rhino and Grasshopper, it changes on your device. And then the gestures and sensor data and how you interact with that model on your device, that gets streamed back to Grasshopper. So you can use it to update your parametric models, change the geometry in those models, send it back to your headset, and build, you know, interactivity into models, which is really, really nice. So you can use Hologram to do all sorts of stuff. You can use it to make assembly sequences. You can use it to make design tools. You know, really, it's an extremely powerful prototyping toolkit. Anything you can do in Grasshopper, you can now do in mixed reality. And that's definitely going to be like way, way faster than trying to build things from scratch in game engines for the HoloLens. It's just a much more accessible toolkit. So I'll give you some examples of what I mean by that. So this was years ago now, like 3 years ago. One of the first things that we did with the HoloLens was building a darts game in Rhino and Grasshopper. You can totally do that. But you'd never think to make a darts game in Rhino or Grasshopper just because it wouldn't be that fun to play on a screen. But in mixed reality, one of the first things that you want to do is pick up a digital object that you see and just throw it just to see what happens, to try to understand the limitations of this virtual space that you're in. I finally managed to hit the bullseye there. The other thing that you can do is build multiplayer applications. So, you know, it's possible essentially to have 2 people or 10 people modeling into the same Rhino environment at the same time. So again, this is all built entirely just with Rhino and Grasshopper. It's a little application. It's a bit like Minecraft. It lets you copy a layer in Rhino and then paste the objects in that layer anywhere in space. And any mobile phone or HoloLens that's connected to Rhino can do this. So you can have multiple people all tapping and placing these blocks, and it just becomes like a collaborative modeling exercise. which is really, really great for engaging people who maybe aren't actually experts in those modeling tools within design processes. Speaking of not being experts, we've had a lot of craftspeople and artists start engaging with using Hologram for making small objects. So this is an example of just, using a 3D model viewed through the HoloLens to show how to fold quite complex 3D shapes together, or using again a 3D pattern projected onto the folded steel object to show how to paint like quite complex enameling patterns onto these objects. We've had artists who work primarily in virtual reality use the HoloLens to fabricate these objects. So this is Jeff Farquhar Still. He designs these crazy complex 3D curved objects that are really difficult to make from drawings. And with the HoloLens, you're able to just look at them in 3D space and fabricate them, just as easily as anything else. You can interact with kangaroo simulations in mixed reality. So that lets you do things like run one-to-one full-scale physics simulations for simulating things like tensile nets. It's possible to run, robotic simulations from Grasshopper and align the coordinate space of the robot with the coordinate space of the HoloLens. So you can preview robotic toolpaths and things like that in mixed reality to avoid clashes or to anticipate exactly how a robot's going to move through its joint space. All of this is very possible and very simple using Hologram with Rhino and Grasshopper. All right, so that is the full shebang in terms of the context, like how we got to where we got to. Now I want to show you, I think it's 2 or 3 projects in the next 20 minutes or so, to just try to, I guess, convince you of the effect and impact that mixed reality is going to have on design and fabrication. And we've done a few of these demonstrator projects that have gotten more ambitious and more complex over time. The first one that we did was in 2018 at Tsinghua University in Beijing, where we just built a pretty simple little pavilion structure, but we designed it, did all the design review, all of the fabrication, all the assembly, and all the post-build analysis entirely in mixed reality. So we were trying to sort of prove that it was possible to do this end to end. So this is the design. It's like a very deliberately complex thing. It's a bunch of woven bent steel rods. They all kind of thread through one another. It's a real kind of tangled mess. And we're just trying to make something as formally complex as we could at the time. So that was the design. And this is where we were building it. And because the place where we were building it, like the site's pretty complex and the object we're making is pretty big, we wanted to make sure that we'd actually be able to fit all of the parts we're fabricating through this space and get it to the exhibition. And what you're seeing here is just the 3D scan of the space that's built up on the HoloLens as you walk around. So the HoloLens is always creating a 3D model of the space that it's in. You can stream that point cloud straight into Rhino and Grasshopper and use it to determine, okay, like, will our part actually fit up this ramp? Is it going to fit under this soffit to get it into the exhibition space? We'll be able to fit it around the columns. All of those things are just really, really useful to know with the HoloLens. And again, or with this project, sorry. And again, we were able to just determine them just with a site walk with the HoloLens. Another thing that we did was to just make sure that this structure was buildable. So it's really, really hard to understand, something that's composed primarily of curves when they're just projected flat on a 3D screen. So things like just being able to see how these curves would join, whether or not we were missing joints or whether we had too many joints or whether the parts were intersecting, whether we needed more connecting pieces. All of this was just way, way faster if you were able to walk around the 3D object than it was spinning around it on screen. And so what you're looking at here is both of those things happening at once. So I'm walking around wearing the HoloLens and just marking up this object. The markups are streamed straight back into Rhino. And then Cam was able to change the design model in real time, and I could just approve it. I could say, yep, that looks better. That's done, it's fixed. And so it's just a super, super fast review process. Then to fabricate each one of the parts, we had very little budget. And so we built all of these parts with an extremely cheap bender that you see in the background here. And because each one of the parts was unique, what we did is we had a holographic guide which showed the geometry of each one of these bent pieces. And we had an interactive application that let us step through the individual bends in each one of those pieces so that you could just focus on that specific fabrication information, like one thing at a time. Just like with the Boeing diagram that I showed you earlier, the critical important thing you need when you're fabricating something with a HoloLens is to just minimize the amount of digital information you're showing to help you perform some otherwise complex, challenging task. So here we have the students following these holographic guides, bending these pieces. You can see up here, there's the interface they're using to step through these individual bends. And to fabricate each part, it's really, really simple. All you're doing is lining up the physical pipe after it's been bent with the virtual pipe, and then just bending it around until it continues to line up. So here you see them doing that bending, they bend it around. Once it lines up with the hologram, you know it's right. So there's no measurements, there's no drawings, there's no labels, there's no templates, there's no jigs, there's no nothing. Just bend it and then assemble it. So normally you'd have something horrible like this. You'd have tons and tons of parts with all of the joints and the parts labeled. Clearly all these parts are a mess. It's really hard to tell them apart. Your digital model on Rhino looks like this. It's also just a spaghetti mess. It's super hard to tell which part is which and how they're supposed to go together. The physical object while you're building it is also a mess. It's kind of floppy until it's all been assembled. It's really, really hard to see where everything is supposed to go. And so the only way that you can assemble these kinds of structures really is with having a holographic guide. So this is another student. She's got a part which is going to go into the structure. And what she sees on the HoloLens is a like holographic model showing exactly where that part is supposed to go. And she's using her own intuition, as you can see here, for how she needs to weave that part through the structure in order to get it to fit and match that holographic guide. So that massively simplifies the documentation that we need to do. We can rely on the fabrication team to make like intelligent decisions during assembly and build things up without a cumulative error. So here you can see the red piece. We had another really, really simple interface that lets you step through the current piece being assembled and just check that they're all in the right place. Once it had been built, we wanted to digitize it to make sure that it was precise, or at least to be able to say how precise it was. And yet again, as always, we used the HoloLens to do that. So we were able to track a marker with the HoloLens, like just a printed fiducial marker, and take the tracked position into Grasshopper and essentially just place points in space and redraw the curves of the physical structure so that they exactly matched the curves. So they exactly matched our, we had a digital model that exactly overlaid that physical object. So then we could compare what our original digital model was, so the model that we used to fabricate the object, which is this one here, with our digitized model, which is this one here, also showing the deflections, and just measure the difference. So this is before build, this is after build. And then that's the actual physical thing. So what we found was the maximum deflection of this object, I think was about 25 millimeters, and the average was 16 millimeters. And this is from 16 millimeter tube. So that precision, I think, is, well, for something that's made entirely by hand by people who are using the HoloLens and a bender for the first time, entirely acceptable. We've also tried working with the HoloLens on construction sites. So not doing really sculptural pieces, but trying to work with industry and with trades, specifically with bricklayers. And the reason that we're able to do this, like, essentially engage trades with new technologies, is there's three reasons. One is it's very easy, we've found, to get tradespeople to engage with the HoloLens because they don't really need to learn any new user interfaces. You just put the headset on. If you see a big button, you can kind of reach out and push it. Like, that's easy enough for anyone to do. It doesn't require a lot of expertise just to use the device. The other reason that we've got a lot of uptake is these mixed reality experiences, they're always shared. So you can easily train somebody, walk them through what they should be seeing, walk them through how to interact with the digital content and all the rest of it, just by both wearing a HoloLens, both looking at the same model in the same place. And then the last reason we've got a lot of uptake from industry is basically because the HoloLens, up to a certain scale, provides you with precise location of digital content in physical space. So it can be used for all sorts of construction tasks straight out of the box, which is really, really exciting. So we tried doing a couple of projects with bricklayers. Initially, we were just doing like really, really simple prototypes ourselves from foam blocks, extremely simple mixed reality applications. So you have 2 buttons that you can interact with on the HoloLens for changing the course of bricks that you see. And you're using that holographic information just to place bricks. It's extremely fast to use these applications. So this was a structure we built of about 4,000 foam bricks. Oh no, sorry, it's about 2,500 foam bricks, I think. And it took about 4 hours to build. It gives you an idea of the precision of these processes, because like basically if any of these bricks are in the wrong spot, they really stand out. And so we thought that was like a good enough test to try doing this at full scale with mortar. And I've just got a little video that shows you how that went. Now this video does have some rude language in it that's not beeped, I think. So if you are offended by that, maybe just mute your audio for the next couple of minutes or so. So this is the project. It's a small feature wall, about 600 bricks. This is the digital model, really simple holographic information, and showing you all the bricks. And this is Colin talking about it.
There isn't a single brick on there that lines up to anything. Every brick is different. This would take you like 2 weeks. Yeah. For one guy, and a lot of that would have to be, you know, made up. Do you know what I mean? You're not going to get it exactly like this would be.
So they're using that same interface. Basically, you have multiple people able to look at the courses of bricks as a hologram, and they could use that for all sorts of things, not just placing the bricks, but also training apprentices in how to do brickwork, which was really, really exciting.
So that's all the bricks, right? Yep. So see how you are here. That one's good. Yep. This one here shows it's got to come round. So just treat that like you do your string line all the way around. Mm-hmm. Hit that back.
And we found that working with the brickies, they were basically developing their own new construction techniques while they were using the HoloLens. So they were able to build this wall in parallel, like multiple people doing it at once, where normally it just have to be one really skilled guy. And they figured out how to make that as quick as possible. So they had Colin going through and roughly placing the bricks, and then Ben going through and neatening them up, like you see here, getting them exactly right. And they just take so much care and precision in this work. Like, this is not just about doing something faster or cheaper, it's about doing something better, which is what you'll hear Colin say.
I once seen a program on John Lennon, you know, and he reckons every song that he made, he used to get scared that, fuck, I'm going to stop now because I'll never make anything better than that, you know. That's how I'm thinking, fuck, it's time to stop. I'm nervous that I can't make nothing better.
And we'll come back to Colin at the end of this talk, so I'm just going to keep moving on. Now, another project that we've done, like the most ambitious one by far, was to try to upscale the use of mixed reality. So, you know, larger than the brick project, larger than that bent steel project, in the design and construction of this pavilion in Tallinn. Now, this pavilion project was a collaboration with just so many people. So the design team was myself and Cam Newnham from Fologram, along with Sumin Harm and Igor Pantic, who were both at the Bartlett at the time, and format engineers. So pretty large design team. And then we had an enormous team of volunteers and friends who basically helped us with prototyping and flew to Tallinn to help build the project as well. And what I want to talk about is basically to convey the idea that working in mixed reality allows you to be extremely ambitious and take massive, massive risks in experimental architectural production. And I wanted to prove this, I guess, by talking through like really the background of this project and showing you a lot of things we did that didn't work out before showing you sort of the end result of this process. a lot of the work that went into this pavilion as well was digital. It was behind the scenes. Like we had to solve a lot of quite complex problems. And I'm going to share a few of those digital approaches with you too. They're not really related to mixed reality in any way, but I think they're kind of interesting. So the idea with this this pavilion originally was we thought that we could use mixed reality to really efficiently set out formwork for steam bending timber pieces. So usually with when you steam bend timber, it's a really time-consuming, tedious, expensive, and difficult process, mostly because you have to make a one-off mold for every single part that you're going to bend. And then after you've bent it, the material always sort of springs back into a different shape, and so it's really hard to make parts precisely. We thought we could solve both those problems with mixed reality. We thought we could have a really efficient way to set up formwork, so it would be cheap and fast. And we thought we could use the hologram to see just how much our parts were springing back so that we could just adapt that formwork until the parts would spring back into the right shape. We thought there was a great opportunity there. And then we also thought like it'd be really fun to try doing something with a sort of traditional craft practice. So, you know, steam bending timber is not something that happens very much anymore. But it's this like really efficient way of making really quite complex forms. And so we thought, well, that'd be fantastic if we could work that out. We'd never actually steam bent any timber before when we started doing the competition. So this was in January of last year, 2019. And we did a couple of prototypes in our studio, just from really, really thin timber strips. So you can see on the right here, this is the kind of a hologram showing some basic formwork. You know, we've got a column, we've clamped some bits of scrap timber to it to set out the shape of these curves. And then you can roughly follow these curves, both using that formwork and the holographic guide to try to form this shape. And so then on the left, you can see like the physical attempt at doing that. And we thought like, yep, that's that's good enough. It vaguely works. Like now let's just be as ambitious as we possibly can with the design. So we were interested really in, like this is an early sort of sketch from the competition phase, again in about January. We were really interested in capitalizing on the language of curvature of the timber. We knew the timber would have to twist. We knew we could work with different kinds of, like different species of timber, of wood. And so we get lots of different qualities and characters just by playing with that. And over time, throughout the sort of design phase, we basically gave up on the idea of building this. We thought, well, you know, the idea is quite strong, but we don't actually know how to steam bend anything from timber. We don't know what the constraints are. So let's just do a project which demonstrates like the formal potential of this application. So we really dialed the design complexity up to 1,000. And the idea was we'd have these sort of chunks that we would make from timber strips, and those chunks would somehow come together to make this large pavilion. And then we did some sort of nice renders of it on the site. And when this project was like, when it was actually awarded, when we were asked to build it, it was published on Arc Daily, and there were a lot of comments, just people just saying, this is just impossible to build. Like, why has this been selected? The end result is going to be so different. And we shared that. We should definitely shared that opinion. We had no idea how we were going to build it. It was extremely ambitious. Again, like I say, we'd never steam bent anything from timber before, but the jury who selected the proposal, I mean, we can't thank them enough, really. I think it's so rare to find a jury that awards and supports really high risk experimental fabrication approaches. And so they gave us the opportunity to do our absolute best to try to figure out how to build this thing. And because in the end it worked out, we're extremely thankful for that. I think, yeah, if we ever had the opportunity to work with these guys again, we'd be really excited to, because they have the right attitude to risk for sure. So after we'd been awarded the competition, the first thing to do was to figure out how to solve the springback and how to actually steam bend full scale timber. So we built one of these kind of custom scaffolding jigs that we'd imagined during the competition phase. So now we're looking at sort of, this is in March of 2019. And we were trying to steam bend these strips. So you set up this scaffolding following a hologram, and then you put the timber in a steaming box, which we built ourselves. You sort of steam it and then try and bend it over the scaffolding. But what happens is when you take it off, you can see in this little GIF on the right, the black is the shape of the timber when it's on the mold, and we're not bending this very much. And the red is the shape when it comes off the mold. So it basically springs back into its old shape. And this is just a huge, huge problem. Like, you can't make large, like building scale components out of things which are just the wrong shape. And so we needed to figure out a way to solve this problem. We really didn't want to just end up cladding some substructure. We thought that was a real cop-out on the original kind of premise of the project. And so we had to find a way for the structure to work as a shell, just using like very, very minimal parts. So the initial idea was we would introduce rigidity to these parts, or these timber parts, by doing them in pairs. So, you know, what you see here is we have like formwork, which is laid out on the ground instead of using 3D scaffolding. And then you bend a piece of timber over that formwork, you attach a bunch of steel bracing to it, and then you bend a second piece of timber around that bracing. So now you have two pieces of timber with this bracing in between them. That forms a sort of rigid composite, and it can't spring back as much because the timber is, the steel pieces, there's basically pinning it in shape, or at least that was the idea. So we did a prototype. This is in April now, April or May in 2019. No, it's May in 2019. And this is our new formwork system. So we've just got pieces of timber now bolted to a false floor, or screw fixed to a false floor, sorry. Those pieces of timber are set out following a holographic guide. So you can see these colored parts. They're showing what kinds of formwork need to go where. And then there's this sort of yellow holographic strip, which is showing you the shape the timber needs to be. And then there's a piece of actual timber underneath that yellow holographic strip. So we've managed to fabricate and bend a piece of timber into this same shape. So making one piece like this was like, we proved that was possible. And all these parts are pretty short. They're just little parts, and then they all get assembled together into these like larger composites. So we made this huge prototype in 2 days. And this was at Temple University with Andrew Witt and Chris McAdams, Tim Rosterholtz, and James Pazzi, and then a whole lot of really fantastic students. The prototype, essentially, it sort of worked. I mean, you can see here we're getting these sort of sweeping complex curves, but it was incredibly difficult to manage the spring back of the timber at the ends of the pieces. So within the middle of the curve, we didn't have any spring back because we were pinning these pieces with these steel brackets, but at the ends would just straighten out. And when we tried to join them end to end to make larger chunks, you would just end up with these pieces which were completely different shape to the digital model. So this prototype, even though it's just a 2-day exercise, utterly failed. So we were in May now, and we were due to start construction of the pavilion in July, and we still had no idea how we were going to build it. We could steam bend small parts, but that was about all we could do. So in June, we did another prototype in another architecture school elsewhere in the world. So now this is at Aarhus in Denmark. And this is with Ryan Hughes and Dagmar Reinhardt and another bunch of really fantastic students. And this time we had the great idea of, rather than breaking the pavilion up into small pieces and steam bending them individually, we'd do the opposite. We would try to make each of the pieces as long as possible so that you would never have joints end to end between pieces. And you would steam these entire long, like 12-meter long parts in a big plastic bag and then bend them while they're still hot so that you just completely eliminate all spring back. And we did a test, and we also changed the wood we're using. So this is with European ash. The European ash, when you flat saw it, bends really well. You can basically tie it into knots, like you can see on this image here. And so we knew now that we could actually fabricate pretty much all of the formal constraints of our digital model. So this is what our digital model was looking like by now. It's sort of in June again. It had been rationalized so that every single piece of timber in the project spanned between 2 footings. So you'd have a piece start at 1 footing, go through, curve around, swirl around, do what it has to do, and then end at another footing. So you could pin both ends and steam bend, and then you have like a 12-meter long piece of timber, steam bend it into the right shape in between the two of them. So that's how we had to rationalize the digital design. But we still rationalized it into something that was pretty goddamn complex. Now, this rationalization was extremely difficult to do because we knew that there was going to be a whole lot of challenges when we were fabricating this pavilion. So it's one thing to digitally model things. It's much harder to digitally model things so that they actually behave in your digital model the same way they will when you physically manipulate a part. So because all of our pieces of timber are these bendy, springy things, we really needed to make sure that what we were modeling in Rhino was something that was going to actually form into the same shape as our physical timber parts, because there wasn't any point drawing anything that couldn't actually be bent into a shape. But that was just one of the many, many constraints that we had when we were working with these timber pieces. And that's because every single one of these timber parts, because of the budget of this pavilion, every single one of them was made from exactly the same dimension of timber. So we just had timber boards, which were all exactly the same length and width and thickness. And that was, we just used those exact same timber boards to form every single one of these parts. There was nothing was laser cut or CNC cut. There's no, prefabrication of parts. Everything had to be made from these straight lengths of timber. And so because of that, we just had all these constraints we had to somehow digitally model. So we had to make sure that we weren't modeling anything where the curvature of the part exceeded what we could bend, so we'd minimize breakages. We had to make sure nothing intersected in the digital model because we weren't going to cut any notched joints or anything like that. We had to make sure that the boards all unrolled to a straight section to guarantee that we could make them from straight planks because we weren't laser cutting anything from sheet. We had to make sure that where the boards, like where there were lap joints between these boards, because they were 12 meters long, that all those lap joints weren't in areas of high curvature. We had to make sure they were spaced apart so you could get a drill in there to assemble all the brackets. Had to make sure they were all accessible. There's just tons and tons of constraints around what was going to actually make this thing possible to build. And rather than modeling each one of these constraints, like just drawing it, what we ended up doing instead was simulating them all. So what we first did is we made a model, a digital model that would approximate the shape of these timber strips. So this is what you see with these colored lines in 3D. And then we used a physics simulator to make sure that all of those fabrication constraints were actually being solved. And the most important one was that these 3D curved timber strips would unroll into straight or as straight as possible sections, so we can make them from planks. And what was really, so I think I was going to run this simulation again. You can see here how the geometry of the board is slightly changing because the physics simulator is trying to do two things. It's trying to make the board actually fabricatable. So it's changing the shape of it so that it unrolls straight, but it's also trying to make sure that it matches the design intent as closely as possible. So it's not changing too much. It's this negotiation between what we drew, what we want, and what is actually possible with the material that we're working with, which is really interesting. Now, this isn't actually a great way to model normally because the end result is only approximate. Like the boards don't perfectly unroll straight. And sometimes they slightly intersect and everything is like rough. It's almost right, not exactly right. But because we're fabricating everything by hand using a hologram, that just doesn't actually matter. We only have a certain amount of precision that we can hit when we're working with a holographic guide anyway. It's exactly like that steel chair that I showed you earlier. It's about capturing the design intent as closely as possible and minimizing the risk of some large, massive mistake. More so than it is about digital precision. Nothing is about digital precision in any of these projects. It's about using the digital model to avoid the chance of catastrophic failure of during construction. So this is how we modeled all the timber strips. So basically by trying to simulate how material would behave, whilst also trying to simulate matching preconceived design intent. So these parts were sort of 12 meters long. We also used a holographic guide just to show exactly where the parts would need to bend. So the color that you see here is showing the curvature of the part in 3D. So when we were laying up these boards, we could see, okay, it's going to bend a lot in this region. I'm going to make sure that I put like a really nice piece of timber in this region where it's bending. And where we have crappy cheap timber that's split or has knots, I'm going to put that into regions where it's not bending too much. And this is coming back to that point I made earlier about using kind of, let's say, non-standard materials in construction. So we were able to use really low-grade timber because we knew how we could distribute our material to minimize the risk of things actually, breaking. Steel brackets in the pavilion, pretty similar deal, just tons and tons of constraints that we had to model. Again, these are all these brackets were made out of just 40 mil flat bar. So there was no digital fabrication of any of these either, no laser cutting, no CNC cutting, everything's just a standard length of material. But they were much, much, much more complex to model because all of these timber boards, the constraints for the brackets is you always want them to sit on the inside. They have to connect boards as much as possible. You need to be able to actually fit them in the structure. They need to be bendable with an analog bar bender. There were just an awful lot of constraints for these brackets. And so the only way to fabricate these as well was to, again, try to use a physics solver to digitally simulate a few of these constraints. So what you see here is, again, we did a kind of a rough model. Just basically it's a parametric model to try to get the bracket as good as we possibly could. And that then has a whole lot of problems with it. And you can see that it's not properly touching the boards. It doesn't unroll straight. Some parts of it, like some of these bends are too tight to be bent. And then the physics solver just goes through and tries to remove as many of those constraints, or tries to solve as many of those constraints as possible by adjusting the bracket geometry to make the part unroll straight, whilst still trying to maximize the design intent, like the shape of the bracket that we actually wanted. All right, now let's see how the whole thing was built. So we've got about 5 more minutes in this presentation, I reckon, and then we can do some questions, hopefully, or you can all go to sleep, a long day. So how we fabricated these parts is you have a holographic guide showing you the shape of each strip. The 12-meter long piece of timber is in this bag. It's extremely hot. It's getting steamed all the time during bending. And you're just using like a team of people to gradually guide this piece of timber into the shape that you see on the Hololens. And then you're just clamping it off in place. So the only information that you actually need for fabrication is just the shape of the part in Rhino, which is pretty amazing. Like when we first started building the pavilion, so this is in July now, we initially were showing where all of the formwork has to go. Later on in the process, we just showed just the strip, and we made up the positions of the formwork just by eye, matching the geometry of that strip. This is showing bending each one of the brackets. So it's a bit like that pipe bending before. You have a simple application showing you the exact geometry of each one of these bends, as well as kind of a simple user interface so you can step through each one of the bends. And that let us build all the brackets by hand from stock 40 mil square bar, or flat bar, sorry. And you have a hologram on site showing you how everything goes together. Now the hologram on site is super important because the whole structure is made from flexible materials. It deforms under self-weight when we did all the engineering analysis. The individual parts, even though you can precisely steam bend them under their own weight, they also take a completely different shape than the shape they're supposed to. And so the only way that you can assemble something together from these parts, because they're so flexible, is it's sort of more like weaving something into a hologram that you see than it is just assembling like Lego bricks or something like that. It's this process of really massaging material into a desired shape. And that's exactly what we did. So this is sort of seeing the structure on site, these huge long parts standing up in the sky, just trying to gradually weave these steel and timber pieces together. So the language of this pavilion, we hope, expresses how it was made. So it's trying to show and capture the qualities, again, the flexibility of this timber material, and sort of demonstrate the capacity for enormous variation that's facilitated by an incredibly simple fabrication process and production chain. Like it's just one length of timber and one length of steel. And the simplicity of the tectonic system as well, I think, is really important. So it's just a shell, but that shell does all sorts of things. So a wall becomes, like an interior surface. A column can become this kind of canopy. everything is sort of twisted and lashed together. And the sort of differences between these architectural elements just gets really blurred, which I think is one of the most kind of captivating effects of the structure. And then the twisting of the strips creates all these really nice plays with light and shadow. And the twisting is like just as much a product of the fabrication process as it is something which is, you know, just modeled and intentional. If anything, it's more a product of the fabrication process than anything else. So just a couple of views of the structure, some views of the interior, and then the finished thing. So I think that this pavilion, like what we're trying to do really is, again, to come back to this polemic position regarding kind of like digital fabrication or industrialized construction. Like we're trying to show what's possible just by leveraging like human craft and intuition and traditional approaches to making like very, very simple production chains, one type of material, or in this case, one kind of timber, one kind of steel. And yet you're able to produce like wildly complex formal outcomes. And all of this is also done under extremely tight time constraints and extremely limited budget. I mean, we're only able to do it really because of the incredibly generous support of a huge team of really fantastic volunteers who traveled to Tallinn and donated their time. But I think it's also a product of just not needing to rely on, the reason that this project is possible really is we just were able to eliminate all of the risk by not having to rely on prefabrication of any of the parts. Like if we made a part wrong or it didn't fit or it broke or whatever, we were always able to just remake it again because we're working from a very standardized kit of materials and because anyone can put the HoloLens on and assemble any of these parts. So all of the skills just become really evenly distributed throughout everybody on the design team, which is really, really exciting. All right, so to wrap up in a couple of minutes, what's next in terms of mixed reality and especially in industry? We're seeing lots of things happen in industry right now with mixed reality, which is really, really exciting. So companies like Windover are using mixed reality to assemble steel trusses on site. It's like pretty simple idea, really. It's improving like capabilities and skills and reducing risk. We're seeing companies like Art Engineering document projects in mixed reality. So this is a project for Art+Com built by Studio Babelsberg. It's as far as I know, it's the largest structure that's ever been completed just from mixed reality documentation. So, and they documented the whole project in mixed reality again to just reduce the risk and provide certainty that this kind of complex, unusual structure would be built without any mistakes because they were concerned that some of these self-similar parts would be installed incorrectly. With the bricklayers, Colin, that I showed you earlier, we've since done projects on real large-scale construction sites. This is the Royal Hobart Hospital, where we did a whole lot of brick benches using mixed reality guides, so at a much larger scale than the wall that I showed earlier. And this gives you a sense of the scale that's possible to achieve working with mixed reality right now. Everybody always asks, what's the precision? At this scale, the average precision is about 7 mil. Depending on how well you follow best practices, which is extremely important. And all of this, like to sort of sum up, I think this uptake from industry, there's a few things that are just super important to point out. It's not necessarily about making things quicker, faster, cheaper for industry. And it's definitely not, that's not what interests us as kind of designers either, as I think hopefully I've pointed out many times in this presentation. What attracts industry to this technology is that we're finally able to bring some technological change to their industry that improves how they're able to work. It allows them to extend what they can do. It allows them to bring the next generation into their trade, to make their trade more attractive to young people. It improves how they're able to train that next generation. It improves how they're able to collaborate. It improves the skill of their team. It allows them to work better. It makes the quality of their work higher. It provides them with more certainty. It means they make fewer mistakes. And then on top of all of that, it's the saving time and money on jobs. Like that's just the icing on the cake, really. And so this is why I think we're going to see a lot of kind of like pull from industry, demand from industry for these kinds of technologies, because they're healthy for people. They're improving how people work. And I just think that's so important with what we're trying to do here at Hologram. All right, so last thing I wanted to do is point out that we have another fun product. It's like a virtual studio space that you can try out if you want. It's called app.studio. If you want to share models with anyone, give app.studio a try. It's pretty fun. We worked on it through the pandemic. But generally, thanks so much for your time, and hopefully you're not asleep and we can take a few questions maybe.
Thank you very much, Gwylliam. That was an amazing show of possibilities with mixed reality. I'm really excited. Once we defined that we want to make this festival, I thought immediately in Hologram, because I think it's really, really cool. It changes the way architecture can be showed and constructed. I remember many times in school receiving some feedback from my professors and saying that's not possible to build, and you are showing us that anything can be built with the correct tool. So it's really awesome. I'm really happy that you are here. And well, thank you very much. We open the QA session. If anyone has any question, please, you can raise your hand here in the Zoom, or you can write it down in the Facebook Live, and we will be happy to read your questions. Oh, sorry. Don't worry. Okay, there you go.
Hi. Thank you first, William. I would like you to, well, I actually willing, because now that I see your work and I'm also have a close relation, well, like close experience with Sansar. I don't know if you know the platform. I'm wondering if, do you believe that in a couple of years, it will be like socially required to have HoloLens? Like if you have a cell phone, I mean, like we are using it in everywhere and everything.
I'd be very reluctant to say in a couple of years or to give you any time frame. I'd be extremely surprised if it didn't happen eventually. I just think that it makes a lot of sense. Like we design in 3D and we build 3D spaces. It does not make any sense to have a two-dimensional step in between. Like it's as simple as that. It makes a lot of sense to design in 3D, to document in 3D, to verify and check and communicate and collaborate in 3D, and then build a 3D space, and then manage that 3D space post-build with virtual environments as well. So all of that to me seems very obvious as a future, but when it's going to happen, who knows? Yeah, I'd hope it's in a few years, but I don't. I think my guess would be more like a decade.
Like a decade? Okay. Let's see. Thank you.
Yeah, thanks.
Okay, any other question?
Everyone's really tired. I understand.
Well, that happens every time. At the beginning, they're really shy, and then they start doing a lot of questions when the time is running out. But don't worry, I have another question. I don't know. I mean, I've seen too many options or too many applications with the Hologram app. Is it the same with the cell phone? I mean, anything that you can do with the HoloLens can be done with the cell phone?
Almost anything, yeah. So the idea of sending geometry from Rhino and Grasshopper to your phone or your HoloLens and then interacting with it in some way to change your Grasshopper model and create that kind of loop, that works exactly the same way on the HoloLens and on the mobile phone. How you interact with content is quite different. So on the mobile phone, you're tapping on things on your screen. So you're always holding the phone up and tapping on things that way. Whereas with the HoloLens, you're able to interact in 3D, and that's a lot more intuitive. But otherwise, it's the same. I think the app, we originally made the mobile phone app not to replace the HoloLens at all. It was more so that someone who didn't have a HoloLens could still experience what was being seen on the HoloLens. So you could pull your phone out and see what they were seeing. Like that's a really, I think, important and compelling use case because you can participate in something. And then we also thought it might be useful, like say it's much easier on your phone to like type or to push buttons in a really complex interface than it is on a HoloLens. And so we thought, well, maybe the phone could be like a 2D way of interacting with content you see on the headset. That could be good too. Yeah, so those are the main uses for the phone we see. But of course you can try and use the phone for everything that I've just shown on the HoloLens. It's just you would be working with it's always very difficult to judge depth on the phone. So you'll see something and you won't know if it's like a meter away from you or 2 meters away or 20 centimeters away until you move your phone a little bit. And so it's yeah, it can be it's just different. We had some people in Iran did a workshop with bent steel rod, and they did all of that entirely with the phone. And the way that they did it is all of the bends they were doing were 2D. And then you don't need depth perception, right? Like you can see on your phone the shape that something should be, and you don't have to worry what shape it is in 3D, just in 2D. And you can kind of use the phone just as a very flexible template. So they didn't need to constantly be making drawings and labeling things and all the rest of it. So that seemed to work quite well. But I mean, obviously you could also just do that by printing drawings. So it's not as much of an amazing sort of use cases with the HoloLens.
All right. Thank you. I was wondering, well, we were talking before about the workshop that you gave for Digital Futures. Are those videos still in YouTube? I mean, can we invite people go ahead and check and take that workshop?
Yep, that's a really good question. They are. So if you go to, I think it's youtube.com/Fologram, I think that's our channel. There's not that many videos on there. I think the Digital Futures ones are pretty much the only stuff that's up there at the moment. So if you're interested in learning how the software works, like you have a mobile phone and you want to try it out, that's a really good starting point. You can watch those webinars and just follow along, and you should get a really good sense of how the app works, especially for fabrication. I think that's what we were mostly interested in that workshop. Oh yeah, thanks Isaac.
Cool. And is there like a trial version, or I don't know, like a discount for students or student license? I don't know.
Yeah, another good question. On the phone, it's free. There's a paid version, but the paid version you shouldn't need, or at least that was the intention of it. We thought we'll try and like set a paid tier so that practices maybe would pay for it, but for students, you can definitely use it for everything that you'd need without paying. So yeah, that's all completely free. And then if you're lucky enough to have a HoloLens or a Oculus Quest headset, then there's a two-week trial. So you can try it out. Unfortunately, we can't make the HoloLens software free just because there aren't enough people lenses out there if we gave it away for free. But I mean, again, if you happen to have a HoloLens and you try it out for 2 weeks and you need like another week to finish whatever it is you're doing, you just let us know. We're usually pretty accommodating with people on projects.
Good. So is there like a Grasshopper plugin, or how do we make the bond between Grasshopper and the app?
Yep. So you can go to that address, get the plugin for Rhino and Grasshopper, and that's so basically you can search for Hologram on the App Store. You get the app, and then you can download the Rhino and Grasshopper plugin from our website, and then away you go. I think watching the digital futures tutorials is probably a really good start, because we go through that at the start of the tutorial. I think, or you can always just email me if you really get stuck. You can ask for some help.
That's good. Well, thank you so much. Let me check the Facebook. I think there's no other question though.
Cool. Well, look, thanks everyone for your time. Thanks for being so patient and staying up late. I enjoyed showing you the work, and yeah, if you ever have a chance to work with mixed reality, make sure you let us know what you're doing, and maybe we'll see you in Mexico next time we're on a plane again.
That would be awesome. That would be awesome. I was waiting to see the Acadia Pavilion that you made in Mexico.
Yeah, I should have put it in. Damn, I didn't think of it. There's a good video of that one on our Vimeo page, though, if people haven't seen it. Let me send a link. Yeah, you should be able to find a video of that project there. It was really, really interesting how we built that little tiny pavilion. It was a big experiment. We sort of made it up during the 2 days of the workshop, and it worked out really well. So
yeah, I mean, I wasn't in that workshop, but I was like really excited every time I went where the place that you were building, and I was like, oh my god, I should have chosen that one. And well, I think it was really cool because it had I guess 2 steps. I mean, the construction step first, and then there was like a mixed reality experience, if I remember well. It has like some QR marks, and then the pavilion changed or something.
Yeah, that's right. Yeah, it was really interesting. We were basically making it up. So you just take a piece of timber, screw fix it in place, and then you'd use the markers with the HoloLens to digitize that piece of timber, so you could work out where it was in your Rhino model, and then generate new parts which precisely fit between these parts that you just made up. So it's this nice kind of back and forth between doing something just purely ad hoc, improvised, on the fly, using our waste material. That's why we started doing this project. Actually, we had a whole lot of just scrap timber, and we thought, well, we should use this, and so we just started screwing it together. But when you do that, everything is sort of floppy and flimsy, and it's really hard to join 2 arbitrarily placed pieces of timber in 3D space with a new piece which fits precisely between them. You end up with these messy kind of edge to edge connections unless you cut them exactly right. So that was when we needed to use the digital model to get those compound cut angles right, so the pieces fit between them. So I think there's on the Vimeo page, there's a little video that shows how that works. It was all very approximate. I mean, it only just worked, but the idea was really, really nice. Actually, there's a paper published about it too, in a new book. But I think, yeah, if you search for it, you'll be able to find it.
Awesome. I think Monica Vasquez has a question. No? Oh, I saw that you were raising your hand. Okay. Well, any of you has another question?
Look, it's okay, Isaac. It's super late. I think let everyone go to sleep. If 14 hours is a very long day of lectures. Okay. If anyone has a question tomorrow when they're fresh, just send me an email, and I'm happy to respond.
All right, then. Well, Gwylliam, thank you once again for being here, for taking your time for joining us. It's been an honor, and thank you so much for everyone watching on the Facebook Live and here in the Zoom. So see you tomorrow for the rest of you. We have workshop from Graphisoft, and then we're going to have another lectures. Thank you, Gwylliam, and Thank you, everyone. Bye-bye.
See you, everyone. Thanks again. See you, Isaac. Chat.
Bye bye. Saludos cálidos.
Hasta mañana, hasta mañana.
A mimir.
¿Quién está grabando? Por aquí ya lo paré.
Ay, qué vergüenza.
Creo que Fer, ¿no?
De hecho, todavía está en el live.
¿En serio?
Sí.
Ay, sí. Andrés.